This lesson will focus on comparing linear and exponential functions and finding formulas for both of those. It's a big part of the Gemini curriculum, and it takes a little bit of practice to get the two processes down. We're going to start by looking at data in a table. So I have a table here, and this is from that textbook, but we have f of x and g of x. So my x values, my independent values, are right there, and these are my dependent values for each one. So I have two separate functions. So for each value of x, I have two different outcomes. If we look at f of x, the difference between consecutive entries is constant. If you look at that, the difference between consecutive entries, which means as I look at my y values, 30, 45, 60, 75, 90, they're all going up by 15 each time. So what that means is this could represent a linear function, because my increase, I can't even spell linear today, whoops, is constant. So a linear function. So that's easy enough. We know how to do that. If you were to plot those points, you would get a line because the slope is constant. So let's look at g of x. G of x is a little bit different for each of those values. The difference between them two, they don't step up the same amount each time, but there is a pattern to it. So the difference is not constant, but if we look at the ratios, we can see something. If I take the 1200 and divide it by the 1000, so I take a term and I'm dividing it by the preceding term, that's going to give me 1.2. Well, if I take another group, if I take the 1440 and I divide by the 1200, guess what? I also get 1.2. So there's a pattern to this as well. It doesn't matter which pair you choose, the ratio between these two are always going to be the same. So for g of x, like I just said, the ratio between consecutive entries is constant. So g of x can be represented by an exponential function. Because the values are increasing exponentially as opposed to linearly. So linear functions, they're kind of like arithmetic sequences and series. The difference between consecutive values is constant. The difference between consecutive values is constant. Consecutive values is constant. I'm running out of room here. For exponential functions, the ratio is constant. The ratio between consecutive values is constant, not ration. It's always the consecutive values. Okay, a linear function, we know what that looks like. If it's a positive increase, it's going to be a line. An exponential, if it's positive, it's going to be curved and getting progressively steeper. So here's the meat of the lesson right here. If I have a function that was g of x, which was on the first page in that table, I want to find a formula for that function. We already said it's going to be exponential. So we're going to use our exponential model. Y is equal to a times b, and I'll make that an x up here. Sometimes it can be a t, it can be an x, whatever. But that's my model. So that table gives you a bunch of x's and y's. And I can pull from that table, if you flip back and look at it, I'm going to pull two coordinates. I'm going to pull 20 and 1000. That's one coordinate I can get from the table. And I'm going to pull 25 and 1200. That's the second coordinate. You could have pulled any two pair. So I have x's and y's. I need to find a and b. There's an x, there's a y. There's an x, there's a y. So I need to find a value for a and b. And I'm going to show you how to do that. We actually have to solve a system of equations to make this work, but we can't solve it linearly because these are exponential equations. So I'm going to walk you through the steps to do this. The first step is you're going to set up two equations. You're going to write two equations that look like this using your two coordinates. So, and I like, if I have the larger numbers, I'm going to do them first. So I'm going to take my x and my y, and I'm going to substitute in for x and for y. And the a and b are just going to stay a and b. So here's what this looks like. 1200 is the y, so I'm going to say 1200 is equal to a times b, and the b is raised to the 25th power. And then I'm going to do the same thing using the other coordinate. So that's going to be 1000 is equal to a times b to the 20. So we need to solve that system, but we can't solve it using addition or substitution. That's not going to work for us. What we're going to do is actually think about how I could get rid of those a's. And what we're going to do is make this a division problem. I'm going to divide one equation into the other. So when I divide, what happens is when I divide the equations, I'm going to eliminate a because my a's are going to divide away. The 1200 is divided by 1000. Please don't subtract those two. This is division. And then over here my b stays, but since these are exponents, we're going to subtract. So we divide on this side, we subtract the exponents over here. My a's simplify to 1, so they divide away. And I'm left with 1.2 is equal to b to the 5th power. From there, you're just going to use your calculator and work backwards and undo b to the 5th to obtain a value for b. So we're going to solve for b by taking the root. Here, since it's b to the 5th, I'm going to take the 1/5 root and use my calculator to do that. So b ends up being equal to 1.2 raised to the 1/5. This is calcular notation. You'd have to use that caret, and you would raise it to the 1/5 power. Or you use the root button in math, in the math menu. You would put the 5 in and then call up the square root with the x. You could do it that way as well. So b is approximately a whole bunch of numbers that I'm going to round to 4 decimal places, which is sufficient. I don't have to write all of them out. 1.0371. These little symbols mean approximately equal to. So there's b. Now we have to go back and find a value for a. So think about how we would do that. So a would be found by taking my value of b and using either one of these equations, substituting in for b, and solving for a. So that's all you do. You end up taking, let's say I take this guy here, and I'm going to say, oh, let's see here, 1000 is equal to a times the 1.0371 raised to the 20th. That's just a number. So you would substitute, you put the 1000 in your calculator, and then here's the number you would divide by, and you come up with a value for a. A in this case ends up being, I got to squish it in here, a is approximately 482.25. So to write everything together, we want to tie everything together. We have our value for a, and we have our value for b. So if I were to write this, it's going to be, hold on one second, and let me get some more space. My final equation is going to look like this. Y is equal to 482.25, whatever you're told to round to, times 1.0371 raised to the 20th. That's how you find an exponential function given two coordinates. So just to review that, you have two coordinates, x, y, x, y. Be careful. Sometimes the x values are going to be larger than the y values. You've got to be careful with what I give you. You have two coordinates. You set up your two equations. Y is equal to ab to the x. Y is equal to ab to the x. Then you're going to divide. Divide on the left-hand side. There's the 1.2. Subtract your exponents. Your a's divide away. From here, it's just calculator Olympics. You're going to take the fifth root or whatever that ends up being. You don't take the log of both sides. You don't do any of that. You process this in your calculator and you get an approximate value of b rounded to 4 decimal places. You go back, substitute in, and solve for a. And there you have it. So here's an example of how we're going to create a function given an application problem. At time 0, a species of turtle is released into the wetland, but I don't know how many turtles were released then. But I do know after 4 years, we've got a count of about 300 turtles. And then 3 years later, we've got a count of about 450 turtles. So we're going to first assume linear growth, and then we're going to go back and find exponential growth, and then we'll do the rest in class. Whether I want to find a linear model or an exponential model, I need two coordinates to do that. So pause this video, take a minute, and see if you can figure out the x and the y, two sets of coordinates based on the information in this paragraph. If you looked for your coordinates, you have t is 4 when the population is 300. T is our independent variable, so we have 4, 300. T is going to be the x place, and 300 is going to be the y place. 3 years later, that doesn't mean t is 3. 3 years later, that means t is 7, and my population is 450. So, if I'm going to do a linear model, this goes back to algebra. A linear model is y is equal to mx plus b. You should know how to do that. So, you figure this out. You're going to calculate the slope, and then you're going to find the y-intercept. That's old stuff. And then we will talk about the new stuff in the exponential in a minute. So when you get done, I'm not going to show the work because I think you know how to do it. Your formula, your linear model, which is p, because that's what we're labeled, as a function of time, is going to be 50x plus 50x, I gotta put the x in there, 50x plus 100. So think about what that means. What do you think the 50 means, and what do you think the 100 represents? And we'll talk about that in class. So now we're going to find a formula using exponential growth. I'm going to walk you through this one because it's what I just taught you. We're looking for an exponential model, and my formula is y is equal to a, b, to, in this case, it's going to be t because that's my independent variable. So I have a y, oh, nope, not a y, sorry. I have a t and a y. So this is independent, this is dependent, a t and a y. We're going to write two equations, we're going to divide them, we're going to solve for b, and then go back and solve for a. It's that simple, it's not complicated. It's just different because we're dividing instead of adding or subtracting. So to set these up, I'm going to have 450, there's my y, is equal to a times b to the 7th. I'm going to divide that by the other number. 300 is equal to a times b to the 4th. When I divide those two, 450 divided by 300, that terminates, that's terminating decimal, I get 1.5, and that's equal to my a's divide away, and that's b cubed. So I'm going to start working over here so I don't run out of room. When I take the cube root, so b is going to be the cube root of 1.5. That's approximately 1.1447. That's my growth factor, so this should start making sense. I typically have a growth factor greater than 1 if something is increasing. So this turtle population is increasing, so this should make sense. My growth factor is 1.14. My growth rate would be this part, about 14.5%. That's what you would get here. So there's B. Now you have to go back and substitute in to find a value for A. I choose an equation. If I chose 300 is equal to A times B, 447 raised to the 4th power. All I have to do is divide 300 by that value, and I get A is approximately equal to 174.7. Now, since we're talking about turtles, and A should represent the initial value, I'm going to round this up to the nearest whole turtle, because that really wouldn't make sense to have 7/10 of a turtle. That wouldn't be very nice. So my final formula, y is equal to 175 times 1.1447. T is my variable. That's my model, using an exponential model. That doesn't mean it's correct, but that's my model using an exponential model. So what I want you to think about, we're going to talk about this in class. In year 12, the biologist estimates that there are 900 turtles in the wetland. So there's a third point, 12, 900. You should be able to use that point to determine which model's better, the linear or the exponential model. So think about that, and we'll talk about it in class. This is a very important concept. It shows up again and again in this curriculum. So it's important that you understand particularly this process. It's important that you get this process down and that you remember the linear process. And again, we will cover more of this in class.